We can continue with studying the basic and the generalized principles of counting. And first, we are going to start with the basic principle of counting. Suppose you have two experiments to perform, and we assume that the first experiment can result in any one of n possible outcomes. So the possible outcomes set of the first experiment has n different elements. And for each outcome of the first experiment that we have performed, so whatever the outcome of the first experiment is, when we perform the second experiment, it may end up with n possible outcomes. So experiment 1 can result in any one of n possible outcomes, and for each outcome of experiment 1, there are n possible outcomes of experiment 2. Then, together, if we combine these two experiments, the combined experiment or these two experiments will have m times n possible outcomes. So basically, we are creating a Cartesian product of the sets of outcomes in both experiments, and the combined experiment will have m times n possible outcomes. Now, in order to understand that, we are going to solve a question where we can apply the basic principle of counting. There is a small community that consists of 10 women, and each of these women has 3 children. If one woman and one of her children are to be chosen as mother and child of the year, how many different choices are possible, the question asks. Now, when we intend to solve this question, we are going to consider the selection of the mother and the child as a combined experiment. However, my first experiment is to select the mother among these 10 women. Then after selecting the mother, then I'm going to select the child as a second experiment. The selection of the mother is the first experiment, and how many possible outcomes do we have for the first experiment? There are 10 possible choices that I make. So there are 10 possible outcomes for the first experiment, and after selecting the mother, then of course I will only have 3 possible to select the child, because that selected mother has 3 children. So for each outcome of the first experiment, I have 3 outcomes for the second experiment. Therefore, the combined experiment will have 10 times 3, 30 possible choices. So I can select the mother and the child of the year in 30 different or 30 possible ways. Now, we can generalize this basic principle of counting, and that is going to be called the generalized principle of counting. In this case, we will assume that we have more than 2 experiments. So we are performing more than 2 experiments, and we are going to generalize the basic principle of counting. So let's just assume that we are going to perform our experiments. And the first experiment may result in any of n1 possible outcomes. After performing the first experiment and observing the outcome, whatever my outcome is, it does not matter. If I'm going to perform the second experiment will have n2 possible outcomes. And after performing the second experiment, whatever the outcome of the first and the second experiment is, the third experiment will have n3 possible outcomes, so on and so forth. So these events are going to continue like this. All remaining experiments are going to continue in this manner. And I'm going to perform the last experiment independent of the outcomes of the all previous experiments. The last experiment is going to have nr possible outcomes. Now, if we combine these are experiments, just like we have combined the 2 experiments in the basic principle of counting, in that case, the combined experiment will have n1 times, n2 times, n3 times, so on and so forth, times nr possible outcomes. So we can generalize the basic principle of counting to more than 2 experiments, assuming r experiments, and we have the number of outcomes that we may observe in each of these experiments by multiplying these number of outcomes of all experiments, we get the number of possible outcomes for the combined experiment of these R experiments. Now, this is a question where we can practice the generalized principle of counting. A college planning committee consists of 3 first-year, 4 second-year, 5 third-year, and 2 fourth-year students. There are 14 students in this planning committee. A subcommittee of 4 consisting of 1 person from each class is to be chosen. So we are going to choose only 4 out of these 14 students. Now there is a rule here, there's a restriction. There must be 1 person from each class. So the question is asking me, how many different subcommittees are possible? Here in this question, I'm going to consider the selection of the first year student as the first experiment, the second year student as the second experiment, the third year student as the third experiment, and the fourth year student as the fourth experiment. Okay. Now my first experiment is to select the first year student, and I have only 3 choices here. So the first experiment may end up with outcomes. The second experiment may end up with 4 possible outcomes. The third experiment may end up with 5 possible outcomes, and the fourth experiment may end up with 2 possible outcomes. Now, if I'm going to create the subcommittee under the restriction of selecting 1 person from each class, then this combined experiment may have 3 times 4 times 5 times 2, which is equal to 120 possible outcomes. Considering this restriction, I can create 120 possible subcommittees out of these 14 students, and that is going to be due to generalized principle of counting. Now let's solve another question. Suppose we are flipping a coin n times consecutively. How many different outcomes are possible if each coin flip results either with heads or tails? Now basically there is this experiment. The experiment is very simple, which is a coin flip. And that experiment has 2 possible outcomes. Either I get a head or I get a tail. Now I'm going to repeat this experiment n times. So the question is asking me, what is the number of possible outcomes? How many outcomes do I have in this combined experiment? So in this combined experiment, I have n experiments. Each experiment has 2 possible outcomes. So according to the generalized principle of counting, I am going to multiply these 2 values with each other n times, which is basically 2 to the power n. So 2 to the power n is the number of possible outcomes of this combined experiment, which is again due to the generalized principle of counting. Now finally, we can solve question 5. This is a much more practical question that we can observe in real life. Again, we are going to practice the generalized principle of counting here, but we need to understand the restrictions provided by the question this time. So we need to read carefully, we need to understand the question carefully so we can apply the generalized principle of counting. So here we are going to design a license plate that consists of 7 characters. First 3 being capital letters in Turkish alphabet, excluding yumuşak G, and the last 4 being figures excluding 0. Okay, so we have to create a 7-character license plate. First 3 of these characters are going to be letters, however, excluding yumuşak G, and the last 4 being figures excluding 0. Now, in the first part of question, we say how many different license plates we can create. Now, let's start with the first part. Let's solve the first part, then we are going to move to the other parts. Now, in Turkish alphabet, we know that there are 29 letters. However, we are excluding yumuşak G, if you remember. Therefore, we have 28 remaining letters. And if you exclude 0, there are 9 remaining figures starting from 1 to 9. Okay. Now you have a 7-character license plate. The first 3 characters are going to be consisting of letters, and we have 8 choices for each of these characters. And for the last 4 figures, for the last 4 characters, we are going to choose from the figures, and we have 9 figures excluding 0. So each character selection is an experiment here. And I have 7 experiments. And the number of outcomes of the next experiment is not changing with respect to the outcomes of the previous experiments. Therefore, I will say that my first experiment has 28 possible outcomes. The second experiment, the selection of the second character, has 28 possible outcomes. The third experiment again has 28 possible outcomes. Then the fourth, fifth, sixth, and the seventh experiments will have 9 possible outcomes for each. Therefore, if I multiply these 7 values, I will get the number of different license plates that I can create without using the letter yumuşak G and without using any figure as 0. And that is going to be approximately 144 million. Now, if we go back to part B, it asks how many license plates would be possible if repetition among letters were prohibited. Now, this time there's a restriction. And under this restriction, we need to design license plates. What is this restriction? It says if you use a letter, you can only use it once. You cannot repeat a used letter. So when you determine the first character, the first letter, this means for the next letters cannot be this letter. Under this restriction, we are going to count how many different license plates that we can create. Now, obviously, if you are applying a restriction, the number of license plates that we can create cannot be more than 144 million, right? So it should be less than this value because there's a restriction. This means the sum of the previous license plates that we have created are not going to be considered this time, because there were repetitions of letters there. We need to be careful here. Let's focus on the first experiment. In the first experiment, so far we have not selected any letter. Therefore, we have 28 possible choices. But once we determine the letter to be positioned as a first character, then the second experiment will have 27 remaining outcomes because you have already used one letter and that letter is fixed now. If you are going to perform the second experiment, which is the selection of the second letter, you will have 27 remaining possible outcomes. And once you perform this experiment and determine the second character as well, in the third position, we can only assign one of the letters out of remaining 26 letters. Okay, therefore the first, second, and the third experiments here will have respectively 28, 27, and 26 possible outcomes after previous experiment is performed. Now that repetition can still be applied among the figures, so you can make a repetition of the figures. Therefore the remaining experiments are going to have the same number of outcomes, 9, 9, 9, 9. Now, if you multiply all of these numbers, you are going to get a value which is approximately close to 129 million. Okay, so you see approximately 15 million of the license plates are removed if you are going to apply this restriction. Now, in the last part of the question, it asks how many license plates we can create if repetition among letters and figures were prohibited. So repetition is also going to be forbidden for the figures, not just letters, but also for the figures in the last part of the question. And in that case, we are going to apply the same logic as we have done for the letters to the figures as well. So when you determine the first figure, you have not. However, after the first figure is determined, then you will have to choose among remaining 8 figures for the second position. And after you have selected this figure, again, for the next position, you will have 7 remaining candidates. And after this one is selected, in the last position, you will only have 6 possible choices remaining. Therefore, when you multiply these values, you are going to get something which is approximately close to 59.5 million. You see more than half of the license plates that you would be able to create are removed from the list by this restriction. So this is how we apply the generalized principle of counting if we have repetition restrictions, and this is how we solve that